Hello everyone. In this video, we cover independent events. Given two events A and B, they are said to be independent if the occurrence of one event does not affect the probability of the occurrence of the other event. Let's take a look at an illustration. You flip a fair coin. The probability that the flip is a head equals 0.5. And now you flip the coin a second time. What is the probability that the flip is a head? Since this is a fair coin, whenever you flip a coin, the probability of getting a head or getting a tail should be the same, equal 0.5. So here, the probability that the second flip is a head equals 0.5. What if we add in a condition? The probability that the second flip is a head, given that the first flip is a head. This probability should not change, remains as 0.5. So we have the probability that the second flip is a head equals the probability of the second flip is a head, given that the first flip was a head. They both equal 0.5. And here, it doesn't matter whether the first flip is a head or not. The probability that the second flip is a head remains unchanged. So here we can say that the event that the first flip is a head and the event that the second flip is a head are independent events. Or we are given that the first flip was a tail. What is the probability that the second flip is a head? And the probability should remain at 0.5. So here we have the probability that the second flip is a head equals the probability that the second flip is a head, given that the first flip was a tail. So whether the first flip was a tail or not, the probability that the second flip is a head does not change. So we say that the event, the first flip is a tail, and the event, the second flip is a head, are independent events. So we have the following. Events A and B are independent events if the probability of A given B equals the probability of A. That is, whether we know event B has occurred or not, it does not affect the probability of event A from occurring. Or the other way around, the probability of B given A equals the probability of B. Whether we know event A has occurred does not affect the probability that event B occurred. Let's get back to the formula of conditional probability. We have the probability of A given B equals the probability of the intersection of A and B divided by the probability of B. If event A and event B are independent, then the probability of A given B equals the probability of A. The expressions becomes the probability of A equals the probability of the intersection of A and B over the probability of B. Rearrange the terms, we get the probability of the intersection of A and B equals the probability of A times the probability of B when the two events are independent. So we have the formula. If events A and B are independent events, if and only if the probability of the intersection of A and B equals the probability of A times the probability of B. This is called the multiplication rules in computing probabilities. When the two events are not independent, then we say that they are dependent events. Let's take a look at an example. It is known that 35% of a certain company's microwave require service under warranty. and 28% of its portable oven requires such service. If a customer purchases both a microwave and a portable oven from the company, what is the probability that both items require the service under warranty? Let's define the event. Let A denote the event that the microwave requires warranty service, and let B denote the event that the portable oven requires the service. We can safely assume that the two items operate independently of one another. Then we will compute the probability of A and B. This is the probability that both items require the service under warranty. The two events are independent, so this probability equals the probability of A times the probability of B. The probability of A is the probability that the microwave requires warranty service, which is equals to 0.35. And then the probability of B, the probability that the portable oven requires the service under warranty is 0.28. Upon calculation, we get 0.098. This is the probability that both items require the service under warranty. Let's take a look at another example. Suppose that a box contains 7 red balls and 4 white balls. We draw 2 balls from the box with replacement. If we assume that at each draw, each ball in the box is equally likely to be chosen, what is the probability that both drawn balls are red? Define the event. Let R1 and R2 denote respectively the events that the first and the second ball is red. We need to compute the probability that the both balls are red. And here R1 and R2 are independent. You can verify that the probability of getting the red balls in the first draw and in the second draw are the same. So compute the probability of R1 and R2. Because they are independent, this probability equals the probability of R1 times the probability of R2. What is the probability of R1? The probability of getting a red ball in the first draw. In the box, there are altogether 11 balls. 7 of them are red. So the probability of getting a red ball in the first draw is 7/11. How about in the second draw? After we pick a ball in the first draw, we put the ball back into the box. Because this is sampling with replacement, we put the ball back into the box. So in the second draw, we still have 7 red balls and 4 white balls in the box. So the box contains 11 balls in total. 7 of them are red. So the probability of getting a red ball in the second draw is still 7/11. So P of R1 is 7/11, and P of R2 is also 7/11. So this is the required probability. And upon calculation, we get 0.4050. What if we draw the balls without replacement? So what is the probability that the 2 balls are red? We define R1 and R2 as the events that the first ball and the second ball is red. Because this is without replacement, the probability of getting the red ball in the first draw and in the second draw are not the same. the two events R1 and R2 are not independent. They are dependent. Because we are doing the sample without replacement. So the expressions of the probability of R1 and R2 equals the probability of R1, and then times the probability of R2 given R1. So P of R1 remains unchanged, 7/11. 7 red balls out of 11 balls in the box. How about the second draw? Because we draw the balls without replacement, so in the second draw, the box only contains 10 balls. And if the first ball is red, in the second draw, out of the 10 balls, only 6 red balls remain. So the probability of getting a red ball in the second draw, given that we have already obtained a red ball in the first draw, equals to 6 out of 10. Only 6 red balls remains in the box in the second draw with a total of 10 balls. And therefore, the expression is 7/11, which is P of R1 times 6 out of 10. Upon calculation, we get 0.3818. All right, so that's it for today's video. So thank you for watching. And in the next video, we will talk about contingency table.